So I'll be
Yep.
talking about hierarchical reasoning model. I guess after I have spent some time reading the paper and the conversations about the paper, a big question is how much this even connects to like the usual papers that we talk about, but we will see. Hopefully, it will still be interesting. So my presentation is based mostly, well, it's based equally on the author's paper itself, and then because the paper triggered a lot of interest and conversations in the community, and the authors made pretty impressive claims about ArcAGI performance. The ArcPrice team has done a pretty impressive analysis and ablations on HRM, and they published an article and some code. So my presentation is also based a lot on ArcPrice team's article about HRM. So first, I want to put like just give a very high level overview of what HRM is. So HRM itself, like this thing in the middle with 27 billion parameters, is a hierarchical recurrent neural network. It has two modules that work hierarchically, and we will get to that module slightly later, and I'll explain why I'm deferring attention to this module. But the other important part of the whole system is this outer loop. So this outer loop essentially, in my opinion, is quite similar to how diffusion models work. So basically, we have two latents, ZL and ZH, high-level latent and low-level latent. And these latents represent a solution, and the HRM module refines these latents, essentially refines the solution, and this whole thing goes in a loop. So basically, we make multiple forward passes, which they call segments, through this HRM module. And with each pass, we refine the solution latents, and the solution latents are conditioned on embedded task data, what the task input is. And the gradients do not flow back through this loop. So this loop is entirely a harness around the HRM module. So yeah, basically, when we talk about what the authors of the paper built, I think it's fair saying that it's HRM plus this loop. Okay. So why it triggered so much conversations online and became quite popular paper to talk about during the summer war was that they claimed like further high performance on ArcAGI 1. So that's so this is the official benchmark from ArcPrice team. They did test on semi-private data set on which the authors could not test, and they confirmed that the model indeed is performing pretty well. And the way ArcAGI reports results is that they report accuracy on y-axis and cost per task on x-axis. And as far as cost per task goes, this is not very impressive, but mostly because the way the code released by authors is structured, they have to train on the entire thing from scratch from random weights. And this cost per task reflects that. In other words, when the ArcPrice team ran this, they were training completely from scratch from random weights, and that's why it comes out pretty expensive. The paper authors, they did say that they plan to separate pre-training on train test and then fine-tuning on eval test, and it probably would, like if they do that, they'll probably put them into like fairly cheap per task category with still the same high accuracy. So that would be like pretty outstanding result, but still like the model is 27 million parameters and it competes with the frontier LLMs as far as ArcAGI benchmark goes. The authors themselves, they report results on ArcAGI 1, ArcAGI 2, which is more complex, on Sudoku, and on maze puzzles. So Sudoku, maze, ArcAGI 1, ArcAGI 2. authors do not have access to semi-private data set. They only have access to public eval data sets. So on public eval data set, they report performance of 40% accuracy, which is fairly high. And when ARC price team has retested on semi-private, they only observed a significant drop. And they report fairly high performance on Sudoku and Maze, especially compared to using frontier LLMs, frontier reasoning models. One note about ArcAGI2, the score they report is 5% accuracy, and ARC price team has tested on semi-private dataset for ArcAGI2, and they report only 2%. Accuracy, which they did not consider really impressive. So we will not be talking about ArcAGI2 much because the result is not impressive. So basically on ArcAGI2, HRM is not contributing much, it seems, but it is very competitive on ArcAGI1, on Sudoku, and on Maze. So I'll spend a couple slides talking about how the input of the problems is structured for HRM to address controversy. The controversy was that HRM trains on eval set of ArcAGI.
Sorry to cut in, Dimitri. Could you go to the previous slide? I have a question. Yeah, so to clarify, O3 mini Claude, like they scored 0 on this Sudoku and Maze, or they do not evaluate at all, like there are no scores for them present.
Can you please repeat?
Like I wanted to clarify if like this frontier models O3 mini Claude, if they actually scored 0 or they were just not evaluated on these tasks.
You mean on Sudoku and Maze?
Yes, yes.
So they did score 0 on
Oh, wow, interesting.
On this data set. Again, it's unclear. I do not believe I have seen on HRM authors repository, I have not seen which harness they use for testing O3, Claude, and DeepSeek on Sudoku and Maze. So it's not like really clear if they were testing it on agentic loop or like one shot, like what was it? But the way they were testing it, they're reporting 0.
Yeah, I think transformers are only doing 4x4 Sudokus. I don't think they're doing 9x9 Sudokus yet.
Yeah. Okay. So I'll get back to inputs. So basically, the HRM is designed to solve grid puzzles. The input is represented as a flattened sequence of tokens. Then this sequence is projected into latent space. And then this HRM loop essentially acts as a sequence-to-sequence model. So just going back to like this overview. So basically we have an input. Input is embedded. And then the output is unembedded ZH latent. It's unembedded into output. So basically like we have a flattened input sequence here, and we have flattened output sequence here. So like the entire thing acts as a sequence-to-sequence model. Authors have published 3 checkpoints, which they trained on Sudoku, on Maze, and Sudoku and Maze are essentially single puzzles. Sudoku is a puzzle, Maze is a puzzle, and ArcAGI is a set of puzzles. They don't really have human-friendly names, but basically ArcAGI2 or an ArcAGI1 contain on the order of 1,000 different puzzles. So they released a checkpoint for ArcAGI2, which attempts to solve, is trained to solve all 1,000 ArcAGI2 puzzles. And yeah, this example illustrations, I think everyone knows how Sudoku looks like. Everyone knows how Maze looks like. So with Maze, like there is a maze, and there are 2 points in the maze, and solving the maze means finding a valid path, valid shortest path through the maze. And ArcAGI is ArcAGI problems. Each of the 1,000 or so ArcAGI problems is expressed via 2 demonstrations, and then there is the actual problem itself. So the important.
So each of these. Sorry, please. I was just going to ask about the input, and your slides as input. So.
Yeah. So basically, HRM sees the examples of solving the puzzle input and output at training time, but it doesn't have access to any explicit description of the problem. And it also is not in context learning system, so it does not have access to demonstration samples at test time. So what this means, and I'm basically just getting to the point of this controversy about training on eval. So basically, if you have an eval set of ArcAGI problems, and we pick an eval problem from ArcAGI, this is the only part that HRM will see as an input. So if it has not been trained on demonstration pairs, it will have no idea how to solve this problem. So basically, yes, they do train on demonstration pairs from eval set, but this is absolutely necessary with how the whole system is architected to possibly solve the test pair from eval set. So hopefully that makes sense. So there is no. Yeah, go ahead.
Yeah, so I know for the transformer models, they using in context learning or whatever, they see the previous problems and they have to generalize to this. Whereas this, they're saying that does it generalize? How does it generalize to problems that it hasn't seen?
So it cannot possibly solve a puzzle that it has not seen during the training time. So this is how the embedding works. So basically they take this flattened grid. The grid is essentially a sequence of colors. In case of ArcAGI problem, there are 10 colors and a grid with certain maximum size, which they pad if the particular problem has smaller grid. So this is the input. And then they embed 10 colors into hidden dimension 5 to 12. And then they have a puzzle identifier. This puzzle identifier is essentially a unique entry in a puzzle embedding layer. So basically when they train on, so let's say this is some puzzle ABC with an identifier ABC. So during the training, they will use some embedding to signify what puzzle it is, the same embedding here, and at test time, they will use exactly the same embedding for the test input of the same puzzle.
So the semi-private would be cases that it hadn't seen before.
Yes, for semi-private.
And it can still get...
So for semi-private, it cannot... So the authors cannot provide a pre-trained checkpoint to run on semi-private. So ArcPrice team, they did retrain from scratch with semi-private demonstration pairs to be able to run on semi-private dataset. And like there's another odd thing. So there's on the order of 1,000 puzzles in ArcAGI, but then they do apply a bunch of augmentation scenarios to each puzzle. So they have about 1,000 on the order of 1,000 different augmentation scenarios for a puzzle. So they end up with 1 million puzzles. And they treat each puzzle plus augmentation scenario as a unique puzzle. So they have around 1 million entries in this puzzle embedding layer. So this puzzle embedding layer becomes a 500 million parameters layer itself. So when they say, hey, HRM is only 27 million parameters, that is true, but then there is this input embedding layer, which is being trained at train time, and this embedding layer has 500 million parameters. So there is a question mark about the claims about the actual size of the model. Like what's going on here. And if you go to Hugging Face and look at the weights, the maze pre-trained checkpoint is 100 megabytes, a Sudoku pre-trained checkpoint is 100 megabytes, and RKGI2 pre-trained checkpoint is 2 gigabytes, mostly because of this puzzle embedding layer. So yeah,
I guess
go ahead.
I'm a little confused about what purpose the puzzle embedding layer serves. Like at least that so it is taking kind of metadata about the puzzle and transforming it into some kind of information that will help with the prediction task, right?
So basically, the latent coming out of embedding puzzle embedding layer tells the model what the puzzle is about, because like this is just a projection of the grid, and this vector 1 by 512 is the only vector that tells what needs to be done with this grid.
I see, but it's like fine-tuned on specific tasks, right? Like you said, it's trained specifically on Sudoku.
There is no puzzle embedding layer for Sudoku and Maze, because Sudoku and Maze are just single puzzles, and so they have a separate checkpoint for Sudoku, separate checkpoint for Maze. There is no question what needs to be done. It's just one puzzle. But RPGI contains many different puzzles with different mechanics, so they need this puzzle embedding layer.
Okay, perfect. And the task ID, does that give you information? Like, is the task ID just a random hash, or?
Yeah, that's for all intents and purposes just a random hash, and then transformation index color map, and it's just random information, because it just becomes an entry in this essentially vocabulary entry in this puzzle embedding layer. So it has no passes no meaning to the model. Like from the perspective of the model, each augmentation of each puzzle is just some unique puzzle which it learns how to solve at train time by looking at 2 demonstration pairs.
Cool. Thank you so much.
Which, like, if you think about it, is quite odd, because like, why wouldn't they limit the vocabulary just to task ID and use different augmentations as just different ways of looking at the same problem? Like my intuition is that would generalize better, and this whole puzzle embedding layer would be much smaller. But that neither them nor Arc Price team has done that kind of ablation. But to me, that would make more sense if augmentation is kind of separate, and then they run. So the test time they do when they take the input puzzle, this input puzzle, they apply the same augmentation, the same 1,000 augmentations as they were applying to demonstration pairs, and they de-augment the result, and they do majority voting on the answer, and they pick the answer based on the majority voting across augmentations. But yeah, so this part of how they encode what the mechanics of the puzzle is, particular puzzle from RKGI, is fairly tricky and raises some questions. So there is clearly no data leak, because they're never training on like this test pair here. They only train on demonstration pairs, but with how they do it, they they increase the size of the model quite a bit, from 27 million parameters to 500 million parameters. But then again, looking at this loop, so we have this outer loop going over and over through 27 million parameters, and this in case of RKGI, this 500 million parameters embedding layer is only at play once when we initially project the task input. So we run this 500 million weights once, and then we run 27 million parameters in the loop multiple times. So I'm just describing what's going on here. Not hard to make judgment or tell how important or unimportant that is. Okay, so the cool part of this loop, so we run this multiple times through the loop, and like it's still a mystery what's inside this HRM. We didn't get to that, but the point is that each time we go through the loop, we refine the solution latents. And the way the answer is obtained is by de-embedding high-level latent back into sequence space. So that has a cool side effect of interpretability, because we can visualize the solution as it goes through the loop, and we can see intermediate results. So this is from the paper, the visualization of how HRM plus loop solves maze. So basically, it's time step 1. There is nothing, I guess, and then it kind of explores different paths through the maze, and eventually it refines the solution to the optimal path. And same with Sudoku. So I guess in red, authors highlight incorrect digits, and in gray, they highlight the digits that have been changed between iterations of the outer loop. And gradually it arrives to the correct solution in 9x9 Sudoku. Same with ArcGI puzzle. So this is the example output kind of demonstration. Model does not see this at test time. So yeah, it's more like for us to understand what's going on here. The model only sees this input and the puzzle ID represented as a latent, and it, but we can see it even modifies the input parts of the input, I guess, makes sense, and it tries something and tries and essentially arrives to what appears to be a correct solution. So I think that's a pretty cool feature of this whole refinement loop. A couple more notes about the refinement loop. So they run the refinement loop at training time and at test time. They call it segment. One of the ablations they're making is that they can run more refinement loops at test time than at train time, and there will be a figure about that. And another detail which I will not be talking about is that they have an extra Q head. So basically, in this loop, they have a Q head, which uses this latence as an input. And the Q head tells if it should be, the whole loop should be halted or not. But it appears that this halting through Q head only has the benefit of saving compute, doesn't really affect the performance of the model much. So I will not be talking about it for the sake of time. It doesn't seem to be an interesting, I mean, it's pretty neat part of the system from a technical perspective, but less interesting from what drives the performance on reasoning tasks. So yeah, this is the auto refinement loop during training. So basically for each batch, they do n supervision steps. So these are auto refinement loops, and inside each loop, they train the HRM module using cross entropy between true, between gold output and what is being predicted. So I guess the point of this pseudocode is that there are no gradients flowing back through the loop. It's just that every time we run the loop at training time, we update the HRM module so that these latents, when they're de-embedded, get closer to the true output.
And in that pseudocode is Z like a concatenation of ZH and ZL?
Yeah, it's a tuple of ZL and ZHS.
Cool.
So authors do report how much the number of refinement loops affects performance. So they on Sudoku. So this is from figure 5 from the paper. So they say, okay, if at train time we only run 2 refinement loops, then this is the performance they get. And the cool feature here is that they can increase test time loops beyond 2 on which they were training, and the performance increases. So basically, the idea is that we can increase compute spent at test time, even if at train time we have only done 2 loops. But then if at train time we have done more loops, say 8, it produces better performance on Sudoku, and the performance increases the more loops we use at test time. So it looks like the number of loops, both at train time and test time, is quite important and contributes a lot to performance. And the ArcPrice team did the same kind of testing on ArcAGI1, and they confirm the same. Basically, when the more loops, the more refinement loops, the higher the accuracy is on ArcAGI1. So this is figure 4 from ArcPrice team's article. ArcPrice team has also done another interesting ablation where they were saying, okay, we can vary the number of refinement loops at test time and train time, which matters more. And they found that if they have done a lot, 16 refinement loops at train time, then at test time, it doesn't seem to matter as much. So basically, if you're looking at this one, the orange yellow bar at the very left, then we see that if you have spent 16 outer loops at train time and then only do 1 loop at test time, we get almost full performance out of the system compared to a variable number of loops at train time and test time. So in short, it suggests that train time refinement loops matter more than test time refinement loops. Unclear why. And kind of defeats the purpose of interpretability, because if we can just spend a lot of refinement loops at train time and then just run 1 loop at test time, then we are not really refining the solution anymore at test time. We immediately arrive to final solution. And the question is it even reasoning? Is there anything going on, or is just a single pass through HRM? So another open question. Okay, so I guess we will zoom in on this HRM module now. So what happens inside this HRM, which kind of gives the name to the whole paper, hierarchical reasoning model. Why is it hierarchical? It is hierarchical because it's a recurrent module with 2 recurrent blocks, low-level recurrent block and high-level recurrent block. So normally in a recurrent neural network, we have a recurrent block, we have a hidden recurrent state, and then we condition the whole thing on some input, and then the recurrent block updates the hidden recurrent state. Here it's hierarchical, which means that we have low-level recurrent state / latent and high-level. So both of them are inputs to, so both latents are inputs to both recurrent blocks, but each recurrent block only updates its own respective latent. So basically, the low-level recurrent block that runs every time step takes high-level latent and low-level latent as inputs, conditioned on the task input, and updates the low-level latent. And that happens for a few time steps. And then we execute a high-level recurrent block, which also reads both latents, but only updates high-level latent. And that repeats for a while. And each recurrent block is a transformer block. Authors believe, authors spend quite a bit of time in their paper talking about how this is inspired by human brain and different rhythms inside the human brain. I will not be getting into that analogy. I did not feel like it's interesting enough, and it's only an analogy. Like at best, it's a metaphor. Really, definitely, the brain doesn't work like that. but there are still good reasons for why authors believe this hierarchical recurrent module is superior to regular recurrent networks or to just multi-layer deep networks. So basically, they're saying like, hey, if you look at the regular recurrent module without any hierarchy, then the latent recurrent state changes a lot in the first few passes through the recurrent block, but then stops changing. So basically, they call it forward residuals, and they say like forward residuals, how much the recurrent latent changes is a proxy of computational activity. So if we are using compute well, it means that the recurrent latent should be changing a lot. And if the recurrent latent is not changing, then we are just essentially doing identity transfer passes through the recurrent block. So they're saying like, hey, just the regular recurrent module mostly wastes compute because there isn't much, after a few steps, there isn't much change going on in the hidden state. While in the hierarchical thing where they have two modules running at two different frequencies and two latents, the frequent latent kind of stops changing. The rate of change decreases, but then the high level latent gets updated, and the high level latent is an input to low level recurrent block. So that changes the math that happens inside low level recurrent block. So it kind of starts doing something again. There's again a high rate of change of the recurrent latent and so on. So basically they're claiming that because of the hierarchy of recurrent blocks, there's more useful stuff going on thanks to more compute. And they have some comparison with a deep neural network where they draw analogy between recurrent steps and layers inside the network, and how only first layers and last layers do a lot of meaningful computations and the layers in the middle not, but I will not zoom into that later.
Can I ask, so is this recurrent in the sense that like the L module, the same L module is used again and again, like in a traditional RNN, or is it like unrolled? So you have, you know, step index, you have like 60 L modules that are all different.
So yeah, it's in a totally classical RNN sense. It's exactly the same single transformer block for L module and single transformer block for H module. And between these two modules, they have 27 million parameters.
Wow. Okay. So then it's very small. Then it's just like a few modules that keep on getting used.
Yeah. So just literally two transformer blocks, which are being recurrently called.
Got it. Okay, cool.
And here I was trying to overlay two charts, essentially what's going on. So basically, like while only the low level block is being recurrently called, the change in low level latent decreases. So basically less and less interesting stuff going on. But then the H module gets called, the H latent gets updated, and then in the next phase of only L module updates, we get this thing. Anyway, this is kind of an illustration of why there is more computational activity going on with hierarchical structure of this module. So authors themselves, they say, let's instead of this HRM, which is internally recursive, so we have this 27 million parameters, which are being called multiple times at each forward pass because it's a recurrent structure. Let's just drop in a 27 million parameters multi-block transformer. So basically a transformer with the same number of parameters, but not the same number of compute, because inside we have k times t steps. So basically we have a compute equivalent to k times t times 27 million parameters if it's a recurrent module, but they are ablating by just using a transformer with 27 million parameters. So does that make sense why if we drop in a 27 million parameters multi-block transformer, we get the same number of parameters, but we get a smaller compute. Yeah, because with this we have this internal recurrence, and with transformer we do not have any internal recurrence. So basically, imagine we drop in just a transformer instead of this. So authors do that. And they call it direct prediction. So when they drop just a transformer inside of this hierarchical recurrent module, the performance on ArcAGI1 drops, but still is quite competitive, not too bad. But then it stops solving Sudoku and it stops solving maze. So basically, if you replace HRM with transformer inside this loop, then yeah, Sudoku is not interesting. Sudoku doesn't perform anymore. Maze doesn't perform anymore, but ArcAGI does. So it looks like HRM is meaningful for Sudoku and Maze and less important for ArcAGI problems. And ArcPrice team confirms that. So they also drop in transformer instead of HRM. They still retain this refinement loop. Everything else is the same, and they basically report that the performance drop when they use transformer. So this is transformer, and this is HRM, is not too big. So ArcPrice team is convinced that this whole hierarchical recurrent module is not important, at least for ArcAGI. All right. Okay, so conclusions. Yeah, so as I said, is hierarchical recurrent module even necessary? It looks like for ArcAGI, it's not necessary. We can just drop in transformer, but it seems to be important for Maze and Sudoku. It's unclear what exactly happens with the refinement loop at training time and test time. Why is it important? It appears to be important. ArcPrice team also confirms that the number of refinement loop iterations is important. And I guess the broader question is, can we even tell that this whole system with the loop, does it reason? What is reasoning? I think with large language models, we can tell they reason because we can read the language and it's familiar to us as humans, and we can say like, yeah, as humans, we reason in a similar way. In this case, they call it a reasoning model. And maybe like there is this refinements that we can visualize from the outer loop are a sign of reasoning, maybe not. So that's an open question for me. Can we even call this model a reasoning model? So yeah, this basically concludes my slides. I'll be happy to continue with questions and maybe discussions. Hear what you guys think about it.
Very interesting. I've been hearing a lot about this paper and the controversy over it. Maybe just to zero in on the ArcAGI results. That both Arc and HRM showed. Well, okay, starting here. That cost is for training and inference, whereas all the other costs are just for inference. So that's quite cheap.
Yes.
That you can train it and run it and get such a result.
Yeah. So as I said, authors were going to a couple months ago back in July to separate pre-training on test subset of ArcAGI and then make the code, adapt the code so it can be fine-tuned on a semi-private data set, but there has not been any activity in the repo since then, so they have not done that. But supposedly that probably would push them into like somewhere in here, so it will be like fairly cheap per task, because to test on the semi-private data set, you wouldn't have to train from scratch. You would only need to fine tune on demonstration pairs of semi-private data sets. So that would be quite cheaper.
It's been a while since I've studied RNNs. With respect to training, could you fine tune these models quite quickly, having fine tune them with respect to a new set of ARC prizes that they've never seen before?
That's a good question. I have not seen answer to this question. Kind of a related note is that in the model, I have not talked about this at all, but they have some trick for training RNN. So basically, they do not unroll in time. They have they use this deep equilibrium. So they use implicit function theorem from deep equilibrium models paper. And they essentially say like RNN, when trained, gets to a fixed point. Basically, the input recurrent hidden state is equal to output hidden recurrent state. Basically, got to the stable point, fixed point, and they are training HRM without backpropagating gradients over time. They are only backpropagating through the last calls to H module and L module. I do not fully understand the math, but basically they justify it by saying perfectly trained RNN should have true answer as a fixed point. And they simplify the whole RNN training. So that trick might allow them to fine-tune easier on new data because they don't really need to do this unroll it back in time. But I do not like fully understand what's going on here. I have not read this deep equilibrium models paper, and I'm not familiar with implicit function theorem, so I cannot comment on that. But they do have a trick, a fixed point.
Yeah, if all the modules are the same, it might be quite easy to just fine tune those two modules. But again, I don't know the intricacies of the RNN well enough. They mention all the time 1,000 examples. And is that the case for ARC AGI?
That's a good question. So they do, so basically the data set for Sudoku Extreme is on the order of million puzzles. And then Maze, I believe, is on the order of million as well. I think I have a note about this somewhere from a comment in the repo or.
Well, it says the number of training examples there in the graph. What is that referring to?
So for this specific, so basically they're saying for this particular figure, they are only using 1,000 puzzles from their data set for Maze and Sudoku, even though their data set has on the order of millions of puzzles. And ArcAGI only has on the order of 1,000 puzzles anyway. So this is not a subset. This is like full ArcAGI, but they still augment it with augmentation and it's augmentations. And I believe they augment Sudoku and Maze as well. But in a sense, they are calling this small sample learning because in all these cases, they only have essentially 1,000 distinct, unique problems as a demonstration to train HRM. For these charts, so I think for these charts, they are not using small data regime. They're training on the full million Sudoku puzzles for the other figures. That's what they tell in the paper, but they're not clear which experiments run on full data set and which experiments run on a subset of Sudoku and Maze. They basically saying like for benchmarking, we use the small scale data set, and for other observations about the behavior of HRM with respect to number of loops, with respect to these forward residuals, they use full data set. That's my understanding.
And so they didn't show any ablations on the size of the data set and the performance.
No. There's no ablation like that, no. I guess they're trying to focus on, I guess in a sense, we can look at the ablation because on 1,000 training steps, they say they achieve 55% accuracy on Sudoku Extreme. And then when they are looking at the effect of number of outer loop iterations, they achieve 100% accuracy on Sudoku. So this might be on a full data set. So that kind of your ablation. On 1,000, they're somewhere in here, and on the full data set, they jump all the way to 100.
Yeah. Well, interesting regardless. I imagine it could be quite easy to train and quite quick to train on 1,000 data points.
Yes.
So I want to follow up on one of Don's earlier points, which is like, okay, so this is an RNN kind of, and like, I don't know, I just feel like there's big classes of models that they're not comparing to. Actually, it's like the choice of comparing this to a bunch of autoregressive transformer-based reasoning models. It really feels like you're missing out on comparing to structured state space models, which are essentially also RNNs. And you're also missing out on comparing to diffusion models. So I'm like, these performances are really impressive, but like, I'm just wondering, like, structured state spaces have also been around for a while. So do they mention that at all in the paper?
They do not, in the body of the paper, they did not mention diffusion models once, and the state space either.
Huh.
Yeah, there's no mention of diffusion models, diffusion language models, or even diffusion models. I mean, the inference time looks very much like diffusion. Training is not very much like diffusion, because in diffusion we carefully construct this noisy latents, and here they do not really construct noisy latents. They just start from noisy latents and do forward passes, but still, like, very similar. I agree. So to me, like, this jumps out as diffusion and state space. It's called state space.
Yeah, it would be structured.
Yeah.
Maybe try structured state.
Structured.
Yeah. Yeah, okay, those are the people. Albert Gu is the person that came up with the S4 model is, so if you haven't heard about it, it's kind of interesting to check out. It's basically like Mamba. If you've heard of Mamba, Mamba is kind of based off of S4.
I'm not familiar with that line, but
Okay.
I must close my research gap.
No worries. It's here. It's just kind of a new class of, well, by now it's like a semi-new class of models that was trying to replace transformers by being essentially recurrent and like scaling to long sequence lengths and stuff like that. And they had like their slightly different way of training recurrent models and expressing recurrence, but like lots of similarities to this approach. And so far they've been found to be less competitive than transformers overall. So I think that, like, I'm curious, like, I guess I don't really understand the nuances of all the differences in training or structure or everything, but I definitely feel like it's a miscomparison if these guys just didn't compare to them at all.
Yeah, so they did not compare the only, so that this is the reference to structured space, state space models. So they're saying, like, hey, recurrence has been explored not only for its capability in universal computation, but also as a means to replace the attention mechanism in transformers, which suffers from quadratic time and memory complexity. And that's the, the reference to this paper. That's the reference to this paper.
Got it. Got it.
So yeah, they do not compare with the puzzle models.
Also, I'm curious. So I'm curious what your thoughts are on how this would generalize to kind of more open-ended autoregression, because the puzzles, in theory, you just have to generate a fixed number of tokens to express the puzzle state, right?
Yes, it's strictly sequence to sequence, same sequence size. So they use encoder only transformer block for recurrent modules inside HRM.
Okay, got it. And then their prediction head is what will generate the puzzle from the hidden state?
Yes, so they de-embed their latent into sequence space for prediction. Where is that? Yeah, basically like this little blue head over here.
That
Yeah.
And is that a decoder? Does that take in ZH and does that generate like tokens or something, or?
It is the H. I believe it's just a single embedding layer. Let's see. Output head.
Oh, so it just predicts the whole puzzle in one shot, I guess.
Yeah, like once they have refined the latent, the sequence of latents representing the solution, they de-embed these latents into the colors, and then they unflatten the sequence into the grid.
Oh, wow. That really is so similar to diffusion, huh?
Yeah. I'm trying to find what the expression is for output head.
Interesting. I mean, this is really cool. It's a really, really great presentation, man.
Thank you.
I just like I'm just like really confused about the positioning because I just feels like this kind of lives. This like really should be compared to other models. Like I just forwarded another recurrent neural, the hierarchical RNN approach by Yeshua Bengio. That's like very old by now.
Uh-huh.
And
Yeah, and for me, I was like, once I was done with reading through the paper, I started wondering how relevant is this paper even for our group, but has been resonant enough that I thought it's worth spending 1 million on it.
oh yeah, no, totally. I'm really glad you covered it because I'd seen it a couple times.
I think reasoning is the wrong word they used in the title, at least.
Yeah, does it even reason? Hard to tell.
It's
I mean, I guess like, Meta called their latent thought model that was also like latent thoughts. And they called it I think a latent reasoning model. So it's not like these guys are have invented this term. There's this ambiguity of the term.
no, but they used better examples. I think they used, directed basically graphs at least to show that some reasoning was going on.
Yeah, here the only reasoning that can plausibly human-like reasoning is this refinement if we visualize it across the outer loop iterations, as far as I can tell.
That's true. But I was thinking that too, but like typically then the refinement itself is a conditioning in a reasoning thread that it's part of you generate the tokens and that conditions the rest of the reasoning thread, right?
Can you repeat that?
Oh, I'm sorry. So you said that the refinement across iterations can be viewed as a form of reasoning because you kind of iterate on the graph. or the problem solution. But so they have this de-embedding step where they can generate those intermediate solutions. I mean, in more standard reasoning, the de-embedding and the tokenization then conditions further reasoning steps. So it obviously, like, it's part of the generation. Here, the solutions are just kind of generated to show.
Yes, but basically the entire reasoning within the loop happens in latent space. Yeah. So
Yeah.
the de-embedding is only for visualization and for submitting the solution. And yes, I did confirm that the de-embedding head in the code is just a linear layer. I think.
Yeah, my problem with reasoning is they're such narrow models that don't generalize. So they can find the answer, and yeah, the reasoning within the loop in such a narrow domain for the maze. And it's more of maybe they're using heuristics of some kind that are encoded or some other method, some other word as opposed to reasoning. It doesn't quite fit.
I agree. It's hard to see a reasoning in what's going on here. And there is no any pre-training at all. There is no, and I agree, there is no generalization. So it's trained for specific. Each instance, each checkpoint is trained for maze or for Sudoku, or in case of ArcAGI, yes, for multiple, around 1,000 different puzzles, but all of these puzzles are structured in a fairly similar way. Yeah.
Regardless, I think they're impressive results, scoring on Arc or even in the maze and Sudoku.
Yes, yeah, especially with Sudoku. And the interesting bit is that they were trying to evaluate on Sudoku. I think they call it Sudoku Extreme. So apparently there is a program for solving Sudokus, and this program can assign a score to each instance of a Sudoku puzzle based on how much backtracking needs to be done to solve it through classical search algorithms. So they were only considering very hard Sudoku puzzles. So it's not like it's getting its high score on Sudoku on some simple Sudokus. They seem to have put effort into evaluating on hard Sudoku puzzles.
Mm-hmm. I wonder how the other models compare. It would have been great, but at least for Arc, I don't think Mamba architecture or diffusion models are placing anywhere. So that's a good result.
Yeah.
Dimitri, I know we're over time, but how would you scale after reading the paper? How would you scale this? Would you yeah.
Scale in terms of increasing.
So yeah, would you add maybe a third layer? Would you increase the size of the transformer? Would you increase the number of loops? Would you?
Good question. I guess I was convinced by, so like my personal curiosity is let's replace this whole hierarchical thing with just a regular transformer, keep the outer loop, and see how to get non-zero performance on Sudoku and maze, because it seems very implausible that HRM is the magical piece that defines Sudoku and maze performance. So I'll try to get non-zero performance somehow by dropping in transformer, maybe increasing the transformer size, maybe trying on a full data set of Sudoku and maze puzzles. So I guess doesn't answer your question about scale. It's more like, okay, what I would want to try if I spend more time on this, and probably would do more outer loop iterations at train time, and just eyeball how the solution progresses, and try to understand what heuristics it's using, if any, or if like the first bunch of iterations is just random noise and not a true refinement, and maybe figure out some kind of eval around that, basically to confirm or disconfirm if the first few iterations of the outer loop are doing the refinement or just random, something random and not useful.
Mhm. I think, yeah, we'll probably see some people tweak this architecture to solve at least very specific problems.
And on GitHub and on the Discord, I've seen a few people very much willing to do language modeling, basically in a what's this class of encoder decoder kind of scenario where there is an input and then the answer is being decoded. Well, but I haven't seen anyone doing that. I do not have Fire. It's just I installed new smoke detectors and they're extra buggy.
I don't hear anything.
Yeah, there were smoke detectors going off.
Oh, well. Yeah, no, I guess Zoom noise filtration is really good. We didn't hear anything.
Good. Especially annoying at night. The old ones were perfect. They never had false alarms, but the new ones are very they're what is the name of this receiver? ROC.
Uh-huh. Uh-huh. The AOC curve.
Yeah, it's not good for these detectors. And Alex, thank you for sharing this other related papers.
Oh yeah, yeah. Sweet. Yeah. So I guess Israel, do you have any comments or questions or anything?
No, I'm just enjoying the discussion.
Sweet. Yeah, I guess I need to get going. But I think that, I guess to close, at least from me, from my end, we had some discussion about like whether or not this is pure reasoning. There is kind of a strain of thought in the first reasoning papers that was comparing reasoning with planning and saying like, planning is the result of Monte Carlo tree searches and exploration. And then reasoning is a way to kind of amortize those planning costs and just have a model that will automatically kind of do some version of search, but just auto-regressively. And on a positive note, at least, as those stepwise progressions show, it does look like it's doing some kind of search through the iterations, and it does look like it's progressively getting closer to the goals. So I don't know, maybe we shouldn't be so negative on what isn't reasoning here.
Yeah. What is even reason? But I like the definition that reasoning is a model learning to just do in weights doing the search.
Yeah, I mean, I think that, for a while everyone was obsessed with Monte Carlo, and then R1 showed us that we didn't have to do Monte Carlo tree search, but still, I think it's still part of the planning is still a pretty essential part of the discussion. Okay, so I guess unless anyone else has anything to say, let's close for this week. And next week we're gonna have Israel presenting. Is that true? Let me check the reading form.
Yes, I will present it next week. I should update the list to the papers probably tomorrow-ish.
Awesome.
Yeah.
Well, we're really excited to hear from you. Everyone else, if you have, friends or groups to promote this to, we're in the stage now where we're trying to fill up the calendar. So yeah, I think Dimitri Stella said that we should definitely start reaching out to authors. That's a lot of work, but I'm happy to start doing that as well. Over the next couple of weeks. So see you guys next time.
Thank you. Thank you for
Yep.
your question.
All right.
Thank you. Have a great week.
Thank you
Thanks
so
for the
much, Dimitri.
presentation, Dimitri. Goodbye.
Great.